Okay, so volume is maxed. I am unmuted. I'm going to share my screen. Start. And I think we're in. So the function here, settings. Where is it? Meeting options. You full screen. Still not full screen, but anyway, okay, better. Okay, so we're recording, as I said, the pressure is on to have those assignments marked. So I will start sending feedback this weekend. So you will get a directly a notification on Brightspace, and you get a mark. If you get a mark of, I don't know, like what did the assignments do out of 10? So if you get 5.5 or higher, then you're good. If you get 5 or lower, then you're not good. And in fact, I wouldn't even give you a mark. I'll just say it's not ready. Do it again. So, and then you need to, does it matter? To be honest with you, when I have nothing else to work with and I'm trying to mark your final exams and the labs are all there, but it's hard to tell with the labs, right? So it's not really an assessment tool, and I don't have midterms. And I said the assignments are not worth anything. But when it's time to make that decision, I do go back and look at the quality of your assignment, especially if you're someone who's an A student and all of a sudden you struggle in a course. I will go back and try to find areas to look what happened, right? So do the best you possibly can. I always said it's better to do half of the assignment done correctly. I know you guys are busy. My assignments can be 98, right? It's better to do half of the assignment perfectly, lights out, as opposed to just diluting it and trying to finish them all, right? So you don't have to finish it all, but concentrate on areas that give me something to work with. And the same with the final exam. Final exam will be same as 4, 6, and 9, a combination of 5 questions, or 4 maybe. One of them will be on wires, channel. One of them will be on CDR. Another one will be on general topics, and one will be on equalization. You already know what the final will be, right? And then what is remaining on this course? Well, we really got to finish this section here today. We'll do it in 5 minutes, and then we're going to move on to timing. And then after timing comes the rest, which is CDR and clock distribution. Those are the biggest 2 things for us. Is how do we actually send data at high speed, and how do we recover it on the other side? And how do we distribute a clock? For you, maybe it's trivial, but it's not. And then after we're done with those 2 topics, I know the assignment will come up, and then we will move on into the last one, which is the equalization part as well, right? And that should wrap up the course. Any questions? Labs going okay? Haven't heard anyone complain, so I assume things are moving. I hope to catch up with the labs as soon as possible, and once we start timing, we'll start doing CDRs on Thursday and try to understand what's going on here. So, okay, so let me see, where are we here? Okay, so the thing about, so let me just quickly wrap up this section. We'll move on to section 7. When it comes down to high-speed electronics, as I said, DC block capacitors, as the ones shown here in the middle, are great because it compartmentalizes and separates one side from the other. The transmitter is its own thing with its own biasing, and the receiver is its own thing with its own biasing as well. But in reality, what happens is the moment you introduce that capacitor there, you now have a new transfer function, right? Which is this high pass transfer function you see there. And the part listed here at the bottom, let's go back to red, I guess red works better. And this part here is extremely important because it actually ends up truncating a lot of the data. So making sure the capacitor is as large as possible is very important. But guess what? Capacitors actually don't necessarily, well, capacitors cannot bring noise, right? They're noiseless structures, but they shape the way the noise behavior in a circuit happens. So by having a transfer function that is filtered, you can actually end up causing or having detrimental aspects on the noise behavior of the circuit. So we always say capacitors are noisy, but we also understand that there's no noise in a capacitor, right? Per se. But it is the fact that anything can couple. Well, actually, that's not necessarily true. Let me maybe generalize that into the extent that when you look at a capacitor, I wish I would have actually had a layout for one of the designs that had a page after. So what is a capacitor, right? So you have a capacitor, and typically composed of a spiral plate. And then you got a very tiny circuit here and a very tiny circuit there. And then you end up using a very large C. So that's what we need. Why do we need large C? Because the larger the C, the lower the cutoff frequency. We have cutoff frequency 1 and we have cutoff frequency 2. So these capacitors, the DC block capacitance, will dominate FC1. So we want it to be very large, right? But capacitors, are mini batteries, right? They also can pick up stuff. Capacitors can pick up electric fields. So if anything happens to go nearby, it would actually couple into it, and it will become noisy. So capacitors don't they don't have a noise in the same way a resistor does, but capacitors are noisy structures inside a high-speed electronics because of that. They can pick up a lot of stuff, and they can also end up causing filtering issues that would affect the transfer function of the circuit to areas where, so we actually want to be able to minimize that. In addition to that, we also have situations where the actual capacitor itself, again, given the property of it that the voltage remains fairly stable, constant, it is possible that you can have the data actually controlling the DC. And how does that work? Well, consider a case where you actually have a perfect balance of ones and zeros. Sorry, 0, 1, 0, 1, right? And then you have another case, such as, so that's basically case A here. It should really introduce a new page. Just wait a second here. Page after. Okay, so for case A, we basically have a balance stream, right? And we got equal number of ones and zeros. And I'll do that in red. And then we'll do the DC in black, right? So it's a perfect balance so that the actual DC, it's right in the middle, right? So we got a 0, we got a 1, we got a 0, we got a 1, 0, 1, 0, 1, 0, 1, 0, right? Then case B is a case where you have more ones than zeros, right? And then you basically will have, case where you will do this. And then you will do, oh, sorry, that's the opposite here. What am I saying? Okay, and you would have a case where you have some zeros and then lots of ones, and then like that, right? So what would typically happen in this case is that the voltage will remain about the same, and when you see lots of ones, it's going to start to wonder, and then here it's going to be balanced again, and it's going to start to wonder again, right? And we can actually measure and quantify that. And then case C, is the last case, is where you have more zeros than ones, right? So you're going to have a case where you're going to have still a balanced structure, lots of zeros, maybe a couple ones and more zeros. And of course, still going to be balanced, and then it's going to start to wander down, balance again, and wander even more, right? So this effect of the DC doing its own thing and kind of following the pattern is what we call basically data dependent noise. So we have or sorry, not data dependent. We actually call it pattern dependent noise. And I think we looked at that carefully, but it's pattern dependent noise, which we call it PDN, sorry. And that can be a problem, right? In a typical system, we cannot really control the number of zeros and ones that we do because it's random. That's the nature of the communication that we're trying to do that. But it can also, but that's a difficult thing to work with. But what it can do, it can basically tell you the worst case scenario. And the worst case scenario would happen when you actually have a maximum number of consecutive bits, or what is the acronym they use here? ANSI ID, identical digits, okay? ANSI ID. So it's basically the maximum number of consecutive identical bits. And that depends on the standard that we're using. So if we're transmitting, and then what we have here, I don't know if you've heard this before, the port 609 gang here will be very familiar. The way we transmit is we actually use a pseudo-random sequence generator, right? Or we can call it PRBS, bit sequence. So it's either the sequence generator if it's the clock, and then the data. So this is more a sequence generator, so it's more for the clock, and this will be more for the data, right? Bit sequence as well. And you can have a PRBS with run length of 8, or you can have a PRBS 16, or you can have a PRBS of 32. 32 being the most popular one that we have. And again, imagine that, right? So that is basically 2 to the power 32 minus 1. That's what that PRBS means, right? So if you have, so in 4609, let me ask you, what kind of PRBS do we have, or PRSG? Didn't it look like this? 5, right? So that actually was a PRBS 5. So there was 2 to the 5 minus 1, which effectively gives you the 31 states, right? That you guys saw in 4609. So you can imagine what a PRBS 32, or sorry, PRBS 32 can do in terms of the length required to be able to do that. Why is it called pseudo? So again, this stands for pseudo random. Why do we call it pseudo random? Because eventually will repeat, right? So there's not such a thing in real life, especially now with electronics and the limitation we have, to actually do something that will go forever. So it looks random, but it's fake, pseudo random, and effectively will start to repeat itself. And in 4609, we saw that. After 32 different bit sequences, guess what? It'll repeat it again. Okay, so for each one of these standards, we actually have an ACID number. So for example, if you're trying to do, I think this is probably PRBS 31. Let's assume it is. So I'm going to say, for example, for PRBS 31, ANSI ID is equal to 72. What does that mean? It means that this thing can be random all it wants, but the maximum number of consecutive bits that it can have, so ANSI ID has to be less or equal than 72. ANSI ID has to be less or equal than 72. Because if you start decomposing, then we go back to your 30-year, 40-year analysis, and you start looking at all the frequency components in here, right? What's going to be the fastest transition, hence the fastest frequency component that you're going to have in the system? What transition would that be? The fastest you can possibly go in the system. So let's say you're doing this at 10 gigabit per second. What is the fastest frequency that you can possibly get? So 10 gigahertz. So if you look at it, period, right? So you got period is the distance between two identical points, right? That's the period. But in that period, you have how many bits? 2. So then, what is the fastest speed that you can possibly get? Half of that. You guys agree? Right? So that's why there's actually no clock at. If you look at you look at the sync function distribution. So the fastest transition you can possibly do is a 1 and a 0. Okay, so you're going to have 1s and 0 components, and then there's another transition where you're going to have a 1 1 0 0, 1 1 0 0, right? And that'll be half the frequency. And then you're going to have, and you start to work yourself down and decomposing it. But the lowest component that you're going to have is going to come from these ANSI components, or the maximum number of identical bits. Yeah.
So in terms of maximum number of identical bits, let's say, for instance, positive threshold, like let's say we have like 75, 72. Is that gonna mean like that noise is gonna make the signal wander so much that we can't read it, or like what's gonna happen if I go 75, say, and then go with 50?
So, okay, so what are we going to do with this, right? So we're going to pass this random pattern system through a circuit that has a bunch of capacitors like this, right? And then what's going to happen is that the voltage on those capacitors is going to start to wander around because we have all these decoupling capacitors. And the figure of merit is the I. You're going to have an I, right? And what's going to happen is as DC starts to wander, this thing is going to start to close.
Okay.
Right?
So I open enough for the
So, exactly. So NCID is going to close the I.
So what exactly then you have to use like equalization? Like,
so yeah, so you're getting right to the point. And NCID is going to try to close the I, right? Because there's so many of them and the capacitor is not suitable and it's going to start to wander around. And how is that going to be quantified? Well, if we look at the definition of signal to noise, one of the ways we did it is by looking at Q, right? The Q of the I. We talked about that in class. So the Q is going to degrade, but wait a minute, Q is related to bit error rate, which is a user parameter, right? You as the gaming guy says, I need a bit error rate of 10 to the minus 12. So that 10 to the minus 12 corresponds to a Q. And then again, you just simply will not be able to comply with all the requirements if you have larger number of NCIDs. How do we fix this? Well, one of the ways they do it is by actually, so choosing an AC coupling capacitor is very important. So you have to make it large, but we know making it large is not necessarily does not come with its own drawbacks, which is capacitors are noisy. Even though capacitors don't have internal noise, the same way as the resistor does. So, and then we talked about the percentage of voltage that we are actually allowed to have, because that percentage of voltage is going to come over and manifest itself directly into the I. 6% drop, right? 6% drop out of the full amplitude, but when the signal starts to get smaller and smaller and smaller, you're going to struggle with it. So we need to have the right capacitor, and the capacitor, beyond the scope of the course, we're not going to talk about it, is actually being quantified into this equation here, which is 7.8. I don't know where the 7.8 comes from. Doesn't matter. I actually put the circuit into a simulator, and I basically look at the Q degradation as a function of the number of bits. That's how I do it. But people out there, you're an application engineer, you don't have access to the tools that I do, and this equation comes over and it says, great, now I know what capacitor I do. Now I know that it's 1.8 nano as opposed to 100 pico or less, right? So 7.8 times the number of consecutive identical digits as well, which again, in our case is 72. And then we have the actual bit rate, right? And well, the bit period or whatever, the bit rate is in gigabit per second, and TB is 1 over that as well. And then you also have the termination resistance of the circuit, which is R. Okay, and example shown here for a 3.125 gigabit per second, NRZ, is equivalent to 3.125 gigabaud, or 3.125 divided by 2 gigabit per second PAM4. Start preparing those acronyms. You gotta be careful with, okay? So the size of the capacitor you need is 1.8 nanofarads, okay? Shown right here. Do you know if you were to actually put it on a board, or if you were to put it into an integrated circuit, well, the ones from 4629, the students will know clearly, but you realize how much area a 1.9 nanofarad capacitor would actually be. And then what will be the answer from you? Well, Paul, put it off chip. What happens when we put something off chip? Not only we're introducing a capacitor, how do we connect it? With a bond wire. Wow, there you go. So now you have a series RLC circuit that is picking up not only electric energy, but it's also picking up magnetic energy. So back to your question is, what do we do? Let's say in the system itself, we need to guarantee an NCID of 72, but you have 75. So then what we do is we actually do something called an encoding. You have 8 bits, but we add two more just to help us later. And the way we help us, so we do 8 bits to 10 bits encoding, or 64 to 66. We add an additional 2 bits, and we use those for equalization. So if you have too many ones, I'm going to add zeros. If you have too many zeros, I'm going to add ones. And you do that, right?
So another thing that I put 75 would be how like 72 ones. Then you put like 0, 0,
0, 0.
and then again,
Yeah,
3, 3,
yeah.
1.
Yeah, something of that order, right? And then there's also forward error correction, which I'm not going to get into here, but there's all sorts of DSP techniques that we can do, scrambling as well, right? So, you know, it's interesting when we talk about IP protection, scrambling, and all that. But in my lifetime, as I've traveled around many different places in Canada and work with them, some crazy ideas that comes with it. And scrambling is an interesting one. So in the past, especially dealing with high-speed electronics, I worked with a company that actually was manufacturing in China. And they basically told them in China that the yield was 90%. Okay, well, that's not an easy decision. Ship me the 90%, that's good, and toss up the rest, right? But 3 months later, or 4 months later, they realized that those products were actually being sold on eBay, right? So companies now are so strict about that, they said, ship me 100% of what you fabricate, right? So the protection is so. We've had cases where you know, a company is so worried about protection that they go and fabricate one part in one company and the other part far, far away. And you can never put it all together as well. Or there's a company that specializes in scrambling. What does that do? You guys probably too young to work to know what scrambling was like for us when we were using analog cable. But scramblers, you could buy a descrambler online. You could descramble Rogers. Right? Scrambling was a business back then. We don't worry about that. Everything is just skips and breaks, and we don't need to. All they need is our credit card number, and away we go. We were a little more resilient. We didn't want to keep that credit card at that time. But anyway, Scrambler is a company in Canada that actually specializes in taking your circuit and just smashing it, sending it everywhere, so no one can tell what it is. Because there are companies in Ottawa, Semiconductor Insights and Chipworks, yeah, that actually specializes in actually reverse engineering circuits. So in the old days, now it's all digital, of course, it's all easier to do. And then you can have artificial intelligence platforms that would actually reverse what do you think it is. All that's being automated. But in the old days, you have a room about twice the size of this one. And literally as if it was the scene of a plane crash, you would have little pictures. And you have teams that will be working around trying to decode. And the purposes of that will be, first of all, when you have an IP infringement, and some company, you believe that is actually infringed into your design, they actually acted as the technical, technical point of contact to be able to say, yes, this actually was wrong and they're using the same approach. So this company actually specializes in scrambling. Interesting. Lots of crazy stuff that goes on in all those wars as well. Okay. Companies are very careful about disclosing information. I got students at Siena that are not allowed to take the data and the laptops out of Siena. I got students that are at TSMC that cannot even disclose the results. So now I'm wondering, why would I even send a student there? We have students that spent 1.5 years at TSMC on an internship that was supposed to be for their thesis. They cannot even get pictures out of what they did. So what do you do then, right? So as a student, you have to be able to disclose this. You have to be careful, but it is a lot of stuff. Pre-emphasis and equalization. So, you know, we have issues like channel itself, closing, channel impairments, loss, dispersion, reflection, intersignal interference. And then that's where pre-emphasis and equalization comes into play. And we're going to leave that a little bit more. I think I explained to you in the last lecture, but we'll try to save the excitement for when we do equalization. And I think that's going to be a really cool thing for you, because I am told that when you guys go to Siena and you tell the hiring manager there that you know what an FEC is, and an FFE, and a DFE, and a CTLE, and all the good stuff that comes with it, they're basically blown away. Like, how is it that you guys are learning this, right? So it's actually good, and you guys will have at least a system level indication of what it is. Here's eye pattern diagrams. Just as this is a review, we've seen this before. This one here is handy. Always keep it close to you as well. But what you see here is basically a mask. This thing in the middle This thing in the middle is what we call the mask. Okay, we'll make it red. And then on the outer parts of it, you typically have a histogram. And that histogram is going to have a mean value and it's also going to have a standard deviation, right? And then you're going to have levels that will define the top and the bottom level, the middle level between the noise and the levels of the eye opening. So there will be various levels that will go around there. It is the peak to peak maximum voltage will be one. The average value of X here, so X1 and X0, those levels are also important. And ultimately, you're going to have how much of the eye do we actually see? And that's going to be on different levels. So you're going to have A1, A2, and A3, right? That's fine. And then threshold jitter parameters, you're also going to have threshold crossing jitters, which is basically the jitter measure at a 0 volt for a differential receiver. And those actually are going to help us identify things like, here's, for example, an overview of what an eye looks like, a real eye. Nothing like we've ever shown, right? First thing to do is the difference between two different identical points. We actually call it the unit interval, or UI, right? And the time that it takes for a unit interval defines effectively the bit rate, right? So if you, for example, are doing 25 gigabit per second, question for class, what will be the width of the eye, right? That'll be 40 picoseconds, right? And if you do it 10 gigabit per second, go from there, right? So effectively, you can go back and you can calculate all that directly from these two as well. Then you have the 100% reference, VL high and the VL low. And then, so that's fine. And then you also have the opening of the eye, right? And then you have worst case jitters as well. And that's just basically looking over in the horizontal side, sorry, in the vertical side. On the horizontal, then you have to look at the transition. And then you have your worst case jitters. You have your threshold crossing jitters, and then you have your this peak to peak jitters as well, right? If this becomes relevant to you and you have to worry about being on a final exam, it will be asked in an assignment. So I give you a lot of notes. If you go back on Brightspace, I've been giving you 10 times the amount of notes that I'm giving you here, but the rules for the exam are as follows. First of all, if it's not in this set of notes that I have prepared on Good Notes, it's not, you're not responsible. It's just additional material for me. And out of the material that I've given you here, which look, we're already on page 69, 70. If it's exercised in an assignment, it's very likely you're going to see it in a final exam, right? So that's why the assignments are so important. Here is an example of what an NRZ real system looks like. So you have continuous random state, right? And then those are actually sliced by the Clarke linear recovery, and they're superimposed. And that's what the eye is, with all the impairments. If you have a PAN4 signal waveform, you obviously have 4 different levels, right? So you got 2 bits per symbol, right? And then you're able to cram 4 levels into the same. So you can actually deal with less bandwidth. And here's an example again of what the NRZ does. Eye pattern and the bit pattern. 0, 0, 0. And again, this will be taking a snapshot of the 0, of the 0, of the 0, the 1, and then superimposing on top of it. And as you know, it causes some issues on the edges here, but it's more forgiven if the signal itself is nonlinear. What does nonlinear mean? I keep on talking about nonlinear. What does a nonlinear system mean? So you got some system and you have the input and you have the output and you got some electronics and we're going to call it that you have gain. right? What do I mean by linear?
Linear, I think, is the direction sort of equation that whenever you get a certain equation, you can expect the output to be an equation. But non-linear then must mean that the inner system itself has, I guess, can change, or its characteristic can change over time. Maybe that could affect the output. Like for example, let's say at time 0, I put in input X, I get output Y. At time 5, I might put in input X, but get output Y plus Z.
You have a linear dependence, right? Here's the linear. That's linear. But what happens when you don't, and actually, let me ask you this. Is there such a thing as a linear system? So if I buy, so I know that if I design my own source, I probably will end up doing a bad job. But what if I go and spend $500,000 on a Keysight piece of equipment that they said is ultra high linear, will still be linear? It's never such a thing as a linear system, right? It's how linear you want it to be. So I'm trying to get it. So linearity defines the fact that you're going to have an output that is proportional on a DC plus VIX plus VI X square, sorry, V1, V2 plus V3 X cube and so on. And then now you're no longer dependent only on the fundamental, but you have harmonics, right? You have distorted the signal. So that's actually a nonlinear system. And that comes as a result of adding components like bond wires, because obviously a linear system based on the electronic components is Ohm's law, right? There was a full Ohm's law. You have the input and the output related by your systems, right? But when you have a system like an inductor or a capacitor, that's basically a nonlinear system, right? The voltage and current are not directly related to each other, right? So when you have a nonlinearity into it, error set can actually be more forgiving because you only have to deal with levels, 0 and 1. But when you got a PAM4 system, you have C here, you have 0, 0, 0, 1, 1, 0, 1, 1, 1. Then you got to deal with the rest of it, right? So obvious, graphically, very important when you're actually designing the system as well. Here is the output spectrum. So the PSD, right, of the the power spectral density of the system in decibel as a function of the frequency, which is again 1 over the frequency divided by the bit rate. So it's normalized. But what you see here is again what we saw before, right? That when you have, if you have a 10 gigabit per second, right? The actual maximum frequency that you can get is not 10, is basically not 10 gigahertz. It's 1 over that. It's a 1-0 transition, right? So it's half of that. So you basically have no energy, right, at the bit rate. So when we're designing systems, so Nyquist will tell you that basically the minimum bandwidth to avoid XI is actually half the bit rate. So this is where most of the energy will be. But so this is needed. So let's go back with, so half is absolutely needed. That's basically Nyquist. The second half, this part here, then we got to be careful. How much of it do we need? And what we have to do is we have to basically understand how much contribution and energy the second half actually have to the overall energy of the system. So where do I cut it? And conventional wisdom will tell you that we typically do 0.67 of the bit rate is the analog bandwidth, somewhere along here. Actually, that's probably not up to scale. But I would say, and we're working with the blue line, right? We're only working with the blue line for now. But 0.67 will probably be about here. Why? Because the percentage of contribution that you have up to 0.67 probably already optimized to be the highest. Because the penalties that you will have, and why wouldn't you want to go higher? Why do I need to stop at 0.67? Why don't I go any higher than that? Any insight from you guys? I need 0.5, but 0.5 still gonna represent some ISI, and ISI is gonna manifest itself into transitional noise on the eyes. So I want to get rid of that. And typically, like I said, the figure of merit is 0.67. Why 0.67? Why not continue all the way? Why don't we go all the way to the bit rate? Well, bandwidth limitations, so it will be higher to go to push it higher. And the second thing is noise, right? So if you open up the bandwidth, the noise goes up, right? But you're passing more. So those are the design considerations. Anyway, here's an example of an NRZ. Here's the example of a PAN4, right? And an explanation of that too. So you guys can look at it. We will likely evaluate that, on the next assignment. For this assignment, we now start a new topic called timing, right? Timing is the heart of the circuit. Timing defines when everything happens. When a value is present on a signal line, the amount of timing that we need to hold, and over time, transient effects that are actually happening that come back and, like for example, the reflection from a transmission line. So timing, important. Signal values and events are controlled by the timing. Clock domains. If the clock, if they're too fast or too close, or too slow, we don't have the right information at the right time to be able to make the decision. So, and then that prevents us from pushing the frequency of the circuit that we're trying to do. So clock domains, effectively a bunch of signals bundled with a single clock. That's a problem, because if you have a single clock, that means that at any point on the circuit, you assume that that clock itself is synchronous and it has the same phase. And we know that's not true because of distributed effects. So we're going to learn in this course how to actually do something called a zero delay buffer. That sounds interesting, right? You can buffer something and it will have zero delay regardless of where you place it. Wouldn't it be cool if you had a clock distributed and you do it through the center? You go to the heart. And then how do you send it, right? You can send it into what we know as H, something like that. And then each one of these would actually have a distribution point. And then we can do things like surface mapping around it. And that'll tell us the amount of delay. And there will be another one here and another one there. And then you can kind of see where we're going with this. But there are ways that actually can guarantee that no matter whether you're a point A or a point B, I can actually use something called a zero delay buffer, and I can basically make sure they are synced. So we'll talk a little about that when we understand timing, right? Now, basic definitions of timing, obviously, is skew and jitter, right? So if you have, what is the difference between them, right? So if you have a skew, obviously means that one signal is delayed with respect to the other. Okay? That can be that. So this effectively becomes an issue of phase. One is, phase being as directly related to the. So one is actually offset a little more with respect to the other. The phase of one is lagging or leading the other as well. That defines the skew of it, right? You got a reference clock and you have a receive clock, and it's skewed slightly as well. That's one problem. The second one is jitter. So sometimes we mix them up, right? So if you have a signal appearing on the other end, often there is randomness around the way that it happens. You actually really zoom in into a transition and it's not steady. It's moving, it's jittery. So we call it, right? And that jittery is as a result of, we look at it in the time domain, but it's a result of what's really happening in terms of the frequency domain. So we got a jittery system. And again, that jitter system, all we have to look at the source that we're driving this with. You got a source, which is the oscillator, the heart of it. And this oscillator is in some kind of a phase lock loop, which is driven by a crystal oscillator. And I'm not going to do all the components, but you can imagine we'll do plenty of that in just a few days, weeks as well. But the point is that if I have a perfect sinusoid in time, Fourier analysis will tell us that that's equivalent to a single frequency component in frequency, right? Right? So we got T, and F is 1 over T, and then F will basically be a single frequency component. Gotta get rid of that. My students and I meet sometimes, but I've stopped doing that since the summer. But what happens in reality is that the jitter that you see in time is going to manifest as a perturbation in frequency. So you're not just going to have these perfect sinusoid, but you're going to see all sorts of skirts around it. Okay? And those skirts are actually gain away from the center frequency. So at this frequency, you have a gain, and that gain is typically defined as dBc. What do you think dBc stands for? Have you guys ever heard of dBc? Is the decibel difference of the signal that you're trying to measure with respect to the carrier. And the carrier being the actual oscillator, right? So what that tells us is that I can figure out how much gain I have away from the desired one, which is the carrier at the center frequency. And that number is obviously a negative number because the gain on this outskirts is less than it is over at the carrier. It's a negative number that we express in the form of, let's say, minus 97 dBc per hertz or per root hertz, however you want to define it. So I've actually taken, because I'm interested in if you guys have ever used a spectrum analyzer, right? The spectrum analyzer is basically a window into the system, and depending on how much bandwidth I allow it, that's how much power I'm measuring. If I have less bandwidth, right, you're effectively going to have a higher level, but if I open up the bandwidth, the power is going to be spread across that bandwidth, right? So it's important to normalize that. I don't want to have a case where I'm measuring it and worry about, did I do it at 100 kilohertz or a megahertz? So we normalize the power with respect to the carrier as a function or divided by hertz or root hertz, however we do. That's where this comes from. This number here is basically says that the power level in here is 97 decibels lower than it is at the carrier. And this is something that we call phase noise. And phase noise, as I explained it here, is actually related to jitter. Right? So we got a problem with so the issues that we got here, and why is this important overall as we care about this? Okay, so let's say you have a constellation diagram. You guys have all seen a constellation diagram? I don't have to explain it, right? So let's say you have a quantum whatever. Let's do, and you have multiple quadrants. I'm not going to do it goes on, right? And you have it on the other side too. Constellation diagram here. If the system is noisy, okay, and then of course there's decision boundaries on all of this. I'm going to take, oops, what did I do? How do I get rid of that? Okay, so, and we have decision boundaries in the middle. That basically tells me if the actual bits goes outside the decision boundary, it means that you have an error. And what thermal noise does, so if you have a thermal noise, what it does is it actually turns the system so into a much wider point, right? Don't know what happened there. Let's go back here. Week 7. Oh, is that right? Okay, well, let's do it carefully. So the actual dot will get wider and wider, and that tells us that we have a thermal noise problem. But you can also have a problem where the phase noise is a problem, and that's going to be manifested when you see a little dot with tails. And that tail tells me that it's sort of anywhere in there, and actually that will start to challenge the decision boundaries. So you got thermal. Oh, yeah, you're right. This one has thermal plus phase noise. Hey, that's pretty cool. You know, I could erase. See, now it's not doing it. Oh, yeah, there you go. Yeah. Okay, so phase noise is extremely important because what happens is when and obviously this is all limited by amplitude, right? So you got limits on the amplitude on all sides because, you know, integrated circuits where we're using have a limited voltage. So if I start cramming more bits into it, for example, if I go from a quant 32 to a quant 64 to a quant 128, whatever it is, the A doesn't change. It's just that I've introduced more states. And as I've introduced more states, there's more strict requirements of a decision boundary. And those decision boundaries now will limit how much thermal I can handle and how much phase noise I can handle. That's what I was trying to get at. It's all system driven, how these numbers come about. Okay, the definitions. Jitter is a temporal variation of the clock signal manifested as uncertainty of consecutive edges of a periodic clock signal. It's caused by temporal noise events, cycle per cycle, short-term jitter, and long-term jitter, right? Which is characteristic of any clock generation system you have. When you look at a clock, you're always going to go and say, okay, so if you were looking for a clock for your project, let's say your fourth-year project, some of you have done it before. What are things that you look into a clock? What do you care about? Whether it's a crystal or whether it's an oscillator, but some kind of a clock system. Price, you said? Obviously, price always, yes. Has to be the cheapest solution that we have. And you said stability, frequency stability, but stability can be in many ways. So it can be frequency stability as a function of what? Temperature. Well, the oscillator doesn't have any input, but it has power supplies and all sorts of stuff, right? So sensitivity, but what else? So obviously the dependence on temperature dependence, but it also should worry about how noisy it is, because again, if I connect the wrong clock and I'm trying to do this kind of modulation, it could be a non-starter because I just didn't spend enough time looking at the phase noise requirements of the clock. Right? Typical. So wireless standards like 5G or 6G actually measured something called an EVM, which stands for an error vector magnitude. And what it does, it basically looks at, if you have a constellation and you put it through a system, how does it look in the end and how much error does it have with respect to you initially have? So this is the output and this is the input, right? How much error does it have from one to the other? And that error vector magnitude is actually represented as a function of percentage or as a function of dB. And what I'm trying to get is within the EV percentage, the dB percentage of the EVM, which is proportional to the modulation standard that we're using, we are allowed to have a certain maximum amount of EVM introduced by phase noise. So it all comes down from a higher level, right? I'm doing 512 quant. 512 quant requires an SNR off. That SNR off requires now an EVM off. And from that EVM, a certain percentage is allowed to be from the phase noise. And then from the phase noise, you have to go back and see does the clock itself is able to handle that, right? It comes from a much higher level, right? Anyway, skew is a time difference. One is a temporal variation of the clock signal, and skew is a time difference between temporally equivalent or concurrent edges on two periodic signals. It's just a check, right? Manifest as SE to SE fluctuations. So check what that stands for. Single end to single end fluctuation of clock arrival time at the same instance. Characteristic of clock distribution systems and is caused by spatial variations in signal propagation. Okay, we're not really going to go into latches and flip-flops. We're all very experts about that. But this one here is really interesting because along the path, and this is part of the assignment 2 that I've given you guys, along the path of trying to get how fast a signal can propagate to a system. System is represented here by flip-flops, but it can be anything. And it can be synchronous or it can be asynchronous. But there's different paths in here, and they've actually identified with different colors. The first one is actually the data path. And notice that the data path, so interesting things. Let's spend some time in here. So 3 types of paths. You have a clock path, a data path, and you have an asynchronous path. And typically the asynchronous, we're not really, we don't really analyze it. So the clock and data are typically the ones that we care about the most. We assume that it's there. And there's 2 types of analysis. You can have a synchronous analysis, which includes both the clock and data. And you can have an asynchronous, which that includes only the clock and the asynchronous path. So all of that, right? But interestingly enough, so you always have an asynchronous path, which is the set and clear. Those are free to come up at any time in the timing of it. Then you have a clock path. Okay? And the clock path is actually composed of 2, and notice how there's 2 different colors. So understand that they're not the same signal. It's the same clock, but the signal arriving on the first flip-flop is not the same as the second one. And the other interesting thing is that the path, the data path, does not really care what's coming before. It only cares about after because we assume the data is there. It's really the clock, whether the clock makes it there. So we're not going to analyze this. We're going to assume that the data is ready to go by the time that the clock does. And the delay to the clock is going to determine the maximum speed. Nothing to do with the data before the flip-flop as well. So data path, we have 2 clocks path and we have an asynchronous path. Okay, we also have just standard definitions. Same system here. So we have a clock feeding 2 flip-flops, which we name register 1 and register 2. And somewhere in between, we have a system or combination of logic, as we call it here. And then we have a launch edge, which is the blue. And then we have a latch edge, which is the one shown in red. And then the data is actually valid over a certain period of time, right? So launch edge is the edge when we launch the data from the source. So we launched it here, we got the link, and then we latch it, and we got the link. So we can measure that. And then the latch edge is the edge which latches the data to the destination flow, right? Okay, pretty standard. Now here, we go back to definitions of setup and hold, right? So setup is the median time that the data signal must be stable before the clock ends. And hold is the minimum time the data signal must be stable after the clock ends. So we have to have it ready before and we have to have it ready after. And there's a concept there as well called metastability, which you probably haven't heard before, which we're going to talk briefly about it. But the interesting thing about metastability is actually a figure of merit to define how long failures actually happen in a product. So everything you buy these days, so there's actually a dozen grad courses over in the systems and computer engineering here that actually deals with production reliability, metastability, and they have something called an MTBF, or the mean time between failures. What I want to talk about this now is, hope I'm not losing. What time is it? 12:30. Is that in the past, we didn't care about MTBF. So your 1948 Ford Mustang had an MTBF of maybe 2,000 years. And that's what they're still around. Nowadays, things are engineered so right, and there's marketing issues and all this other stuff, that the MTBF of a product, like say, for example, you buy a Kia car, right? And the Kia car comes with a 5-year guaranteed warranty. I guarantee you that within 5 years plus 1 month, that car starts to break down. So they're forcing you to chip it away, right? So it's because the MTBF is now an actual engineering parameter that you account for, right? So you don't want to design something that lasts too long for various reasons. You know, Samsung is having issues right now that the phones are so good. I mean, I have 3 Samsung phones before the one I'm using. I can get rid of them. So now what they're doing to prevent that, so we have all these useful phones laying around, and your parents or grandparents come over and say they need a phone, say, oh, take one of mine. I just took a customer away from Rogers. They don't like that. So now what they're doing is basically leasing it to you. They don't want you to have it. Want you to have it back at the end of it. But it's all to do, again, with a war of marketing and how you call it to that. We'll talk about that. So the metastability, which is what I'm trying to measure here, is a function of the amount of setup and hold time that we will have in the data. Yes.
What kind of information do you calculate to set up and hold time? Like, for example, like if I have a certain circuit, like let's say 2 clocks that you show here, like okay, what would I need to know to be okay? Well, the setup time must be at least like 2 nanoseconds, and the hold time must be at least like 2.8 nanoseconds.
It's a bunch of different things, right? So you have failure regions, stable regions, and you got time, right? So here's for example the time delay, and here's the clock delays, right? So depending on all the parameters, you can actually define what are the minimums that you need as well. But we will actually do a quick example on how to analyze the minimum setup and hold time that you need. Well, actually, we'll call it, do we have a setup violation or we have a hold violation, which is related to assignment. Hopefully, we'll get to that in the next 20 minutes. Actually, this is an example right here. How do we know how much is enough, right? We'll do that. So, but where were we? We were at so there is a minimum amount of time that the data must be stable before I can sample it. Otherwise, I run into a violation. Then after I've sampled it, there's a minimum amount of time that I can actually need to have it stable or holding it so that the data becomes valid, right? Okay, so that's pretty standard. Let's go back to this one here. So this one here is the time for the data to arrive at the destination register DE. You have the launch state. That's when the clock is launched, right? And then you have the clock to output delay, just the blue. So the clock arrived at the angle here. How long did it take until it actually propagate to the output? So clock to output delay is the blue. Okay, and then so the question is, how long does it take until it actually finally gets down to the second one here? That's the question mark. So you got the clock to output. Well, sorry, the clock is launched. That's the first one, the launch edge, right? Then we have the clock to output delay. And then we have the amount of delay that you have along these combinatorial path as well, right? So we have a combination of different standard gates that you see there. Combinatory logic, right? And then afterwards, we have this T data and the data valid. So the data arrival time is just the sum of all of those. You got the launch edge plus the T clock plus the TCO plus the TC data, right? Pretty standard. Okay. And then the other parameter is the time for the clock to arrive at the destination register's clock input, right? So you have the clock, you have the register to clock, and that's basically the last part of it, is when it actually arrives on the other side. Is the data ready? And will you have enough time afterwards to be able to hold it? Because the question that you asked was actually very complex too, is how do we know setup and hold times? Well, the setup and hold times at the end, because this is the minimum that you need and the maximum that the minimum that you need of hold times, that really defines the clock speed that you can drive this at. Okay. So how do you define the setup and hold times? That's part of the reason why we're actually using FinFETs. Because FinFETs are smaller. And because they're smaller, they have lower requirements for setup and hold times so that we can drive them faster. It's all to do with speed. Okay, so we talked about this, and then the minimum time required for the data to get launched into the destination register, right? So we'll do an example so we can identify it. So the data must be valid on the red curve, on the last edge is on the orange path here, but the data must actually be valid a little longer. So that's effectively the delay. So you see one effectively delays, but then you have to subtract the setup time. That's what the data must be valid, right? And the data required, the minimum time required for the data to get latched into the destination register, okay? So you have the data must be valid before by the amount of the setup, and then it also must be balanced after by the amount of the hold. You have the clock, the delay, setup as a negative, and hold as a positive. And all the definitions are shown here, right? And then you have something called a setup margin. So let's put it all together. So we go back to this figure here. You see that you got launch edge and the latch edge on the clock. Okay. And then there's delays. Then you have the amount of delay that it took from the clock to get to the first flip-flop, register 1, which is shown in magenta here, the clock 1. Then when it gets to the clock, there is a delay from the time that arrives at the input of the register for the mix to the output, which is called TCO, which is the blue. Then the data goes to all of that delay, which is the glucose, whatever color you want to call it. And then after the data, which is again is delay, needs to have both a setup time and also a hold time on the other side. And the amount of time that we have, the excess time that we have is actually called the margin. Because we know that the clock from here is going to be delayed, and we know there's a setup time, and then the difference between when the data arrives and when you actually need to have it set up is what we call the margin, right? Everyone sees that? That's basically your setup slack. So this can be bunched up into different ways. Now we know graphically what it is. But setup slack is really about when the data gets there. Sorry, the data required time, which is the data required time is effectively the latch edge, sorry, down to minus the setup time. That's the data required time. And then minus the actually data arrival time, which we did through here, 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 and that's when the data was actually ready. So setup slack is the data required time minus the data arrival time. But the data required time can also be written down as the clock arrival time minus CSU minus the data arrival time. Okay. And then if we go back into the clock arrival time and start superimposing all those definitions that I put, is really the latch edge plus T clock 2 minus the setup time minus the launch edge plus TC clock 1 plus TCO plus T data. So if you compose this, what you come up is a very useful, interesting curve here that says the overall setup slack is equal to the latch minus the launch. But wait a minute, that's the period of the whole clock, right? That's one cycle. The clock skew, which is the difference between clock 2 and clock 1, and the data path. So is one period minus the clock skew minus the data path. So there you go. That's actually tells me that if I want to drive, if I want to drive this fast enough, then I need to have a given setup slack. What my constraints are with respect to the setup, but my constraints are with how much phase noise, how much skew you can have, not phase wise, how much skew you can have between the different clocks, and how fast is the actual data you're transmitting, which has to do with the miniaturization of the gates. Does that make sense? Okay, now setup hold times and metal stability, and then we'll do an example. Where did the example go? Actually, let's do the example here first. So you got the circuit here composed of, surprise, surprise, you have two flops, flip-flop 1, flip-flop 2. You got combinatorial logic between, which is that inverter. I don't know what this number is, but we're probably going to assume that it's 6 here. Okay, so T min is 6 and T max is 9. And then you have a clock that is basically set. And then, by the way, these are not, you notice the one on top is actually an inverter. The one at the bottom doesn't have the little dot at the end. So what is an inverter without, what is a triangle without a little dot called? A buffer, right? So it's just a buffer. So we're buffering. Why do we buffer a clock? So it is possible, but very dangerous to actually. Yeah. So the answer here is probably to match the delays. You're right, right? But even then, there's still uncertainty. Most likely is to have the right driving power, right? Because all these clocks driving at high speed is the same as driving RF energy or power to a transmission line. And the power attenuates. We know that, assignment 1, right? And there's phase differences and all sorts of stuff. So, but notice that there is a buffer there. Okay, so let's go back and says, does this circuit have a setup or a hold violation? We got minimums and maximum delays. And every time you look at these in a data sheet, you're going to notice that they have a minimum and a maximum number, right? So hold analysis states that when a hold check is performed, we have to consider two things. The minimum delay along the data path and the maximum delay along. So worst case scenario for the data when we're doing hold, right? So the data gets really quick. And how late can the clock get there? In a nutshell, that's all it is. Do we have enough hold? So the data will get there super fast, but the clock will be late. If we do the opposite, which is a setup, we're going to actually do the opposite. Now, the data gets really late, but the clock was there too early. And do we have a hold violation, right? All right. So, and then we go ahead and start using basically the same equations that I've given you, right? So the data path. Okay, what is the data path? So the data path is basically you have the clock, and then you have the output, clock to output. Then you have effectively flip-flop 1. Then you have the inverter, and then you have flip-flop 2. Notice that we don't care about what's happening before flip-flop 1 on the data path. And the delay in the data path, you basically have the minimum. Remember, it's the worst case scenario. The data gets really fast, but the clock is really late. So you got the minimum wire delay for the clock into the flip-flop, plus the minimum clock to output delay of flip-flop 1, plus the minimum self delay of the inverter, plus the minimum two-wire delay or QL FF1 to inverter of FF2, right? And again, if you do that, you have 1 plus, P clock Q minimum is 9 nanoseconds and maximum is 11. So you got 1 plus 9 plus 6 plus 1 plus 1, right? Because you have you got a 1 here, you got a 1 there, you got a 6, you got a 9, and you got a 1, right? So 1 plus 9 plus 6 plus 1 plus 1, and that gives me 18 nanoseconds. Okay, that's the delay in the path, and that's the fastest that it can go. The clock path is actually, and the decision is actually made on flip-flop 2. So we actually analyze the clock 2 on flip-flop 1 to understand that how fast will the data propagate. But the decision making in question here is actually what's happening on flip-flop 2. So for the clock path, it's effectively the clock plus the buffer plus the flip-flop 2 to clock, right? So if you do that, the clock path is basically the maximum of the wire delay from the clock, the maximum delay of the buffer, and the maximum delay from the clock to output of FF2. If you do that as well, you're going to have, you got your 3, you got your 9, you got another 3, and then you have effectively on that one, you have the 2 as well, right? Which is the hold. We're doing a hold violation in here. So we got 3 plus 9 plus 3 plus 2, that gives me 17. Okay, and as expected here, the whole slack is, again, TD minus T clock, or the time of the data minus time of the clock, and that gives me 18 nanoseconds by the time the data gets there, and 17 nanoseconds by the time the clock gets there. So no problem. The clock's going to get there before we are there, so no issue. We still have an actual positive pulse lag, which is 1 nanosecond. Yeah.
I don't understand why we use the hold time when we calculate the time per clock, but there's no hold time of 2 nanoseconds. Why? Because there's no hold time, for instance.
Because we're doing hold analysis, right?
Yeah, sure. Okay.
And then when we do the setup analysis, that will basically make use of the other, which is the next page. So you guys all see that you have a positive, right? So we have the time of the data to get there, the fastest, minus the slowest on the clock to get there. And we still with that, we have a positive setup hold, right? Now let's do the opposite. What about the setup? How long does it need to be there? Okay, and again, that's the thing. The data gets really late and the clock is really fast. And does the data have enough time to transition after the clock gets there? They said, so what that means is that if the clock gets there too late and the data is already transitioning, it might already be on a different state and you may no longer have be able to hold that value for as long as you need it, right? So maximum delay against the data, minimum delay against the clock. And we go back to the same thing. So the delay in the data path, now doing the opposite, we now have for the delay in the data path of 26 nanoseconds. Okay. And then for the other one, we actually have effectively 20 nanoseconds, except that we're using the setup as well. Okay. So for the previous one was 17, and it's a difference of, so now we have 20 nanoseconds minus 26 nanoseconds, and that gives me a setup slack of minus 6 nanoseconds. And that is a violation. Okay. How do we fix it? Well, we can have a bigger clock period or less maximum delay of the inverter, right? So if the clock period is 22 nanoseconds, then you can basically divide it by whatever difference it is, and you can adjust that. So when you're actually doing analysis on the FPGA, you actually has a similar setup where it tells you how fast you can actually drive things, right? Maximum clocks, or when you're doing an integrated circuit, you can have simple RC tools that will be able to tell you how fast you can actually drive the circuits. But the problem with all of this is the fact that we have, I don't know why I inserted this space here, or where did it go? Here, stability, right? So in a flip-flop, after the rising clock, the transition input is no longer, the transition input data is no longer sensitive, and the output is already developed. So you can have basically clocks and negative clocks, and you can have latches. And then for the proper value to develop, you actually must be connected for some period before and some period after, right? And that's always not always the case. So metastability, again, is a result of, here's a good example on this curve here, right? You got the voltage. You got the voltage on the input side, which is the red. And then you have the clock, which is the clock is the red. And then you have the input, which is the green one. And then you have the output, which is basically Q. So because we didn't actually give it enough time to make a decision, the system doesn't quite know what to do. And you need that state. And metastability really has to do with energy, right? What do I mean by that? I just made a statement that metastability is related to energy in the circuit.
Signal itself, I guess because of the signal itself arriving earlier to the sometimes probably
It doesn't have enough energy to be able to make that decision for us. And we've caused that by two different things. First of all, we start the circuit of energy because we want to design low power circuits. If we crank up the power, things get better, right? In fact, in many areas of engineering, the way we do things are meet the specs, lower the power. Try to meet the specs, and if you do, lower the power. And if you try to meet the specs, we lower the power. That's the process that we do in a lot of engineering to minimize that.
Actually, just in general, like from an engineering perspective, when you design circuits, let's say, whether at work, whether academically, do you have like when you first initially designing your first like prototype, for example, do you have I thought that okay, let me try to design in a way that I can minimize the power, or you just design what you could, and then after you minimize what you could?
So you're in a startup, time is money. So the burnout rate of a startup defines that. So you may not have time to do that. And no engineering place, preferably engineering place, would ever let you design something without you trying to grab as much understanding of it as possible. So we need to grab it in a simulator. That's what we need simulator for. They're more complex in nature and basically tell us what's going to happen before we actually fabricate it. Because we don't want to just fabricate and find out later what happens.
So like in the process of designing the actual circuit.
But your question was about power, right? How do we know low power?
Like when you design something, are you like designing with the Okay, so you must power divided by after divided.
So I said, so it's a good question. I said it before, in the process of developing a product, you need to have at least 3 spin cycles. The first spin cycle is the discovery. You're gonna try to get something to work. The second one is where we figure out, but maybe it was too much power, so it's basically area minimization, or in the case of a PCB, we try to reduce the number of the size of the building materials. In the size of an integrated circuit, we just make it smaller, make it more low power. We try to fix it. And then we send the second spin. And we almost get it like 99% there. And then the last spin is basically when we actually send it for production. So to get to production, you need 3 spins. So yeah, you're right. So the first one, we may have versions. We have version A, version B, version C. The one is more power than the other. We'll contrast things, right? If I don't understand the behavior, I'm going to take that behavior plus minus 10%, and I'm just going to create a version of it. That's what we do. The discovery part, right? And that's the expensive part of doing integrated circuits, is actually those first 2 takeoffs, because we're paying and really not getting any money back. On the third one, then we already have the mask. And I don't know if you know this, but if you know how I said that a 7 nanometer FinFET process is about $10 million per tape out? Well, 90% of that money is the mask. The mask is very expensive. And you got to make separate masks for the tape out 1, separate masks for the tape out 2, and separate masks for the tape out 3. But once you do tape out 3, the one that's for production, those masks are fixed. So you no longer have to pay $10 million. Now you have to pay just a little bit just to fabricate. And then you start buying silicon wafers like crazy. And those masks, the ones that you have perfectionated, are now used to produce a product, right? So the first 2 are very expensive, and that's what actually allows us. But again, the observation interval is important. Energy is important. So this is the reason why feedback. Reinforcing a signal, so you have a 0, 1, 0, and the 0 is reinforcing feedback. You're adding more energy, right? So if you look at a signal that has, just what happens when you have feedback, right? Look at the rise and fall times. When you have a feedback mechanism, the line becomes sharper, faster transition, right? So it allows us to make decisions or to reach that state much faster. Because if you go back to technologies for high-speed electronics, we did say that a feedback system trades off gain forward, bandwidth, right? Again, in the case here, it's basically bandwidth is how fast you can move things around. Okay, so T is the time between clock sampling and the instant when we actually check the flip-flop, and it's known as the observation time here, right? So we can have sometimes things like, look at this one. This is just reinforcement for energy, right? We're reinforcing that 0 because having the right amount of energy into it allows the system to have a better or the ability to react better to the time and the space that we're giving it, right? Now, this can be measured, I said, and the way to do it is by looking at, so we have a clock and we have data, right? Do we allow enough time between the clock being latched and the amount of data being valid as well? And again, as a requirement of that, we need to have setup times and we need to have hold times. But there's other parameters. There's clock frequency. How fast are we driving with the clock? How fast is the data being present? That's the bit rate, right? How much time are we allowing to resolve? Right? And there's also an uncertainty window, which is the setup and hold. We don't know what's going to happen there. We cannot violate. And in the meantime, between failures, it basically means how long would it be before this thing starts to fail? So my claim was that when you bought a fridge from General Electric in 1935, the MTBF is probably 10,000 years. If you buy one from Samsung, I don't know how long you can warrant, 36 months, and then everything starts to go south, right? So that's it. So we can actually calculate that. This is for digital electronics, but in general, this can be for anything. And again, that's equal to E to the T over tau R. So T being the time that we're running, right? The independent. Tau means the resolution time.
how long we're actually getting it. So if we start to plot as a function of t, depending on TR, we'll see how it settles. And then divided by, again, the actual TW, which is the uncertainty window, times the data, the frequency of the data times the frequency of the clock. So what does that tell me? That if the frequency goes up, NTDF goes down, right? If the actual uncertainty window goes up, NTDF goes down. Right, so here is a motivation for, again, moving things higher in the node. Right? So we know the penalty, higher frequency will cause issues. But we know that if you have higher frequency, so if the frequency of the data goes up by a factor of 2, and the frequency of the clock goes up by a factor of 2, but I move from 45 nanometer to 3 nanometer FinFET, and the TW goes down by a factor of 4, 2 times 2 is 4, 1 over 4, it all cancels out. Right? This is from a manager's perspective, that's all they care about.
All right, we're actually over time here. So we'll see you guys on Thursday.